Ladies and gentlemen, welcome to today's lecture. Today, we are going to demystify the internal architecture of a modern smart television or advanced display monitor. By walking through this detailed mainboard block diagram, we will explore how various electronic subsystems communicate and operate in perfect harmony. We will trace the journey of electricity and data, starting from the raw power coming from the wall, all the way to the crisp images and clear sound you experience in your living room. Let us begin at the very foundation of any electronic system, the power. If you direct your attention to the top left of our diagram, you will see the red block labeled power supply. When you plug your device into an electrical outlet, this unit takes the high voltage alternating current, AC, and meticulously steps it down into stable, manageable direct current, DC, voltages. In this specific architecture, the power supply generates two primary voltage lines, 19 volts and 12 volts. The 19-volt line is dedicated to a very specific, high-demand task, driving the display's backlight. It feeds directly into the backlight driver, which then powers the backlight strip. This is what provides the actual luminosity. Without this 19-volt circuit, even if the TV is perfectly processing the video data, your screen would remain completely dark. Meanwhile, the 12-volt line acts as the main circulatory system for the rest of the board. However, the delicate microprocessors and memory chips cannot handle 12 volts directly. It would instantly destroy them. Therefore, this primary voltage must be distributed and stepped down through a series of voltage regulators. Notice the pathways branching off. The voltage is dropped to 5 volts, which is crucial for USB ports and standby operations. From there, or from the main power rails, we have further, highly precise step-downs creating a 3.3 volt line, a 1.8 volt line, and a critical 1.2 volt V-core line. These lower voltages are the lifeblood of our memory and processing units. You will also notice a block labeled street by or standby. This is a vital circuit. It ensures that even when you turn the TV off with your remote, a microscopic amount of 5-volt power continues to run to the main processor and infrared receiver, keeping the system in a deep sleep, ready to wake up the instant you press the power button again. Now that our board has the precise electrical lifeblood it needs, let's move to the brain of the operation, the main CPU society, or system on chip. Located right in the center of our diagram, this is not just a simple processor. In the past, a TV would have a separate chip for processing video, another for audio, and another for overall control. Today, all of that immense computational power is integrated into this single, highly efficient piece of silicon. For this society to function, it requires a few critical supporting components. First, it needs a heartbeat, a steady rhythm to synchronize its billions of calculations per second. This is provided by the XOSC, or crystal oscillator, attached directly to the side of the CPU. Next, the processor needs short-term memory to handle active tasks, buffer video frames, and run the operating system smoothly. This is where the RAM, powered by its own specific voltages like 1.8 volts and 3.3 volts, comes into play. Lastly, the TV needs a place to store its permanent memory, its firmware, your specific user settings, network passwords, and channel information. It needs to remember these things even when the TV is completely unplugged. This is the job of the EEPROM, electrically erasable programmable read-only memory. Notice the lines labeled SDA, serial data, and SCL, serial clock, connecting the EEPROM to the CPU. These represent the I2C bus, an industry-standard, highly reliable communication protocol used by the processor to read and write this essential data. A brilliant brain isolated from the world isn't very useful, so let us explore how this system receives information from the outside world. Moving to the right side of the diagram, we see our modern digital inputs. The HDMI port, the modern standard for uncompressed high-definition video and audio, routes its high-speed signals through an HDMI transceiver before hitting the CPU. We also have a USB hub connecting USB 1, 2, and 3 through a central USB controller to the main processor, allowing users to plug in flash drives, external hard drives, or peripherals. For internet connectivity, which is absolutely crucial for modern smart TVs, the board is equipped with both a wired Ethernet port and a wireless Wi-Fi module. These interface directly with the main CPU, allowing you to stream massive amounts of data for your favorite movies and shows. But what about traditional broadcast television? Look toward the bottom left. Here we have the RF tuner, which receives complex, analog radio frequency signals from your antenna. Because the broadcast signal contains both video and audio woven together, it is split into video intermediate frequency, VIF, and sound intermediate frequency, SIF. However, the central society operates strictly in a digital world of ones and zeros. Therefore, these analog signals must pass through ADCs, analog to digital converters. These components translate the continuous broadcast waves into a binary language the CPU can understand and process. Once the CPU has ingested, decoded, and processed all this input data, it must output it as the picture and sound you can actually consume. Let's look at how it handles the video output first. Follow the lines extending down from the society to the LVDS interface. LVDS stands for Low Voltage Differential Signaling. Because a modern high-definition or 4K panel requires an astronomical amount of pixel data sent simultaneously without any electromagnetic interference, standard wiring won't work. LVDS is a high-speed, noise-resistant data highway. You can see the separate data channels representing the primary colors, red, green, and blue, along with clock and sync signals labeled BVSHS. There is also a VOUT power line connected here, controlled by the PVIN switch, panel voltage input switch. This is a crucial protective mechanism. This switch ensures the delicate LCD or OLED screen only receives power when the main CPU is fully booted, stable, and ready to transmit an image. Sending power to a panel without a stable data signal can cause visual artifacts or even damage the display matrix. Finally, let us look at the audio output. Look to the middle left of the diagram. The digitally processed audio signal is sent via another I2C bus to an audio DAC, or digital to analog converter. This microchip performs the exact opposite function of the ADCs we discussed earlier. It takes the digital audio data and reconstructs it into a smooth, analog sound wave. However, the electrical output of a DAC is incredibly weak, far too weak to physically push the heavy magnets inside a speaker. Therefore, this weak analog signal is routed to the audio amplifier. Notice that the audio amplifier draws its power directly from the robust 12-volt main line. It uses this high voltage to massively boost the analog signal, providing enough current to drive the physical combs in the left and right speakers, giving you rich, loud sound. And finally, at the very bottom right, we have the user interface controls, the IR and key blocks. The IR receiver patiently waits to pick up specific infrared light flashes from your remote control, while the key block registers physical button presses on the TV chassis itself. These blocks send simple, immediate interrupt signals directly to the main CPU, giving you, the user, total command over the entire system. In summary, what may initially look like a chaotic maze of boxes and lines is actually a masterclass in highly organized, logical system design. It begins with robust, heavily regulated power management. That power feeds a centralized, highly integrated processing brain. This brain accepts a wide variety of analog and digital signals from antennas, cables, and networks, processes billions of bits of data a second, and pushes it all out through specialized high-speed interfaces to create the synchronized, beautiful light and sound we rely on for entertainment and information. Understanding this block diagram is the fundamental first step for any engineer or technician looking to master modern display electronics. Thank you for your time and attention today.